our first paper, Martin Leguillon, Sevcek Bermejo, understanding the tensile strength of ceramics in the presence of small critical flow.
And I will present a common work about the strengths of ceramics with Dominique Leguillon from University of Sorbonne in Paris, Olga Sebesek from University of Brno in the Czech Republic, and Raoul Bermejo from University of Leuven in Austria. Okay, as you know, ceramic materials are very brittle materials, and they are very sensitive to the presence of flows, which act as crack initiators. You may find in such ceramic materials some pores, which comes from the processing, and some also sharp flows, which come from the machining of the ceramics. In this work, the aim is to analyze the influence of such small flows on the tensile strength of ceramic materials. Okay, for this purpose, we consider a ceramic material, of course, and a defect, a surface defect, because the surface defects are known to be the most critical ones, and we will consider a small hole, half hole, which we will call it the blunt defect, and we will consider a V-notch defect, we will call it a sharp defect. Okay, the size of the defect is very small as compared to the size of the specimen, quite small. And we assume that if you apply a tensile load on this specimen, you will have the initiation of a small crack in the vicinity of the flow. And of course, this is mode 1, so the crack is unstable, and once the small crack has initiated, you will have the failure of the specimen. To describe this fracture event, we will use the coupled criterion. Just remember that the coupled criterion combines an energy condition and a stress condition. The energy condition simply stipulates that the change in potential energy should be greater than the energy dissipated to liquid crack. And the stress condition stipulates that the normal tensile stress along the prospective crack should be greater than the strength of the material. Combining those two conditions, you are able to determine the crack length at initiation and the critical load which initiates these cracks. Just remember the paper from Dominique Leguillon, a paper from Pietro Gonetti with a slightly different approach, and a recent review with Philippe Weisgreiber in German. Okay, I'll start with the energy condition, which is written here. We define the incremental energy release rate, which is similar to the classical energy release rate of Griffiths, except that the differential increment is replaced by a finite amount of crack increment. So the incremental energy release rate must exceed at crack nucleation the fracture energy, GC. And here we have a scaling coefficient, which is easy to obtain with standard finite elements tools. So you have to perform elastic calculation, and you obtain this scaling coefficient, which is plotted here versus the crack length. Okay, and you can see you have an increasing function. For the stress condition, we have here this expression. So here it is tensile strength. So just a point, this is the intrinsic tensile strength. That is to say, this is the strength you have if you obtain if you do not consider any defect in the ceramic material. Okay? So the scaling coefficient K is plotted here versus the distance at the flow tip. Of course, you have a decreasing function, and the value is higher for the sharp defect because of the stress singularity. And if you escape from the flow tip, you escape from the stress concentration. The value of K is 1, of course. Okay, if you combine those two conditions, you are able first to obtain the critical length at crack initiation. I denote L star. So you have to solve this equation, and this equation I have introduced. It is naturally introduced by the coupled criterion, characteristic length, which only depends on the parameters of the material, the factor parameters of the material. And the second term is here, LC over the size of the defect is the brittleness number, which was introduced by Professor Mantich at the first time, the coupled criterion, a few years ago. So the value of this characteristic length is typically between 40 and 400 microns for ceramic materials. And if we plot L star versus the characteristic length, you obtain such curve. And you see that roughly L star is proportional to the characteristic length. So if you have large characteristic lengths, you have large crack lengths at initiation. Okay, once you have obtained the characteristic lengths, you can deduce critical stress applied to the sample to initiate the crack. This stress will be considered here as the strength of the ceramic material in the presence of the defect. Okay? So to do this, you can apply either the stress condition here, either the energy condition. They are fully equivalent. And in fact, here I report the stress ratio, which is plotted here, versus the size of the defect. Okay, this is the first interesting result. Of course, we have a decreasing function, as expected. If you increase the size of the defect, you decrease the strength of the material. And this black dotted line is here obtained with the standard linear elastic fracture mechanics, assuming the flow has a simple edge crack. Okay? And what is interesting is here that you have a plateau. That means that the strength of the ceramic with the flow reaches the intrinsic tensile strength, that is to say the strength without any defect, if the size of the defect is small enough as compared to the characteristic length. Well, we can plot this in this graph without any non-dimension numbers, just to explain one more time. I select two materials with the same fracture energy, but I change the intrinsic strength of the materials, which changes the characteristic length to 300 to 75 microns. And you can see that you observe, of course, the same effect. You have a plateau, and if the defect is small enough, you can ignore the presence of the defect. In fact, you reach the intrinsic tensile strength. Okay, this is only numerical result, and we would like to compare with experimental data. This is done here using the work of Cook on various ceramic materials. Those authors, they have made a 3-point banding test after introducing small defect with control size by an indentation process. So they carefully measure the size of the defect. They were sure that the defect always initiates from the indentation flow, and then obtain those points here. And if I use the coupled criterion for sharp defect in this case, I get a quite good agreement with those experimental data. So it is interesting to see that we have this plateau as predicted by the coupled criterion. Okay, so one question here may arise. Is it possible to use some experimental data to extract the factor parameters GC and sigma C? So this is what I try to do. I have selected 2 points here from this kind of alumina, and I use the strengths given by Cook and Hall to have this graph, which is a plane GC sigma C plots some isovalues of the tensile strength. That means that each couple GC sigma C here provides the same tensile strength. I have done this for 2 values of the initial cracks length of the defect, of the initial crack flow size, and the intersect corresponds to the properties of the materials. So here you can see that those are the data from Cook, and the estimated data are rather in good agreement. Cook also provided the experimental uncertainties which correspond to the dotted lines. So we can see that we have an amount of uncertainty while estimating those experimental data. The key point here is you have to select first a small defect as compared to the characteristic length. So you will have something which is sensitive to the strength. So you will have an horizontal line. And you have to select as a second experimental test longer defect which will be sensitive to the fracture energy, and you will get an horizontal, a vertical line, and you will minimize the uncertainties for to identify the fracture parameters. Okay, just one last slide. It is well known that the strength of ceramic materials depends on the size of the microstructure. If you decrease the grain size of ceramic materials, you will increase the strength. This is plotted here. This is a standard plot for ceramic materials. I use the data of Chanticoul on alumina. The strength is plotted versus the inverse square root of the grain size. And this is called, and you obtain a line here, which shows that the strength is proportional to the inverse square root of the grain size. This is known as the Oro-1-like branch of this graph. Okay, so this is quite easy to recover those experimental data. Just we have pointed that this limit LC over 10 is the smallest extrinsic flow size, but just we have to consider it is also the largest intrinsic flow size, which depends on the grain size through a factor alpha. So you manipulate this, you obtain this, and you plot this straight curve if you assume that alpha is 0.5. So we are able to recover the Oro-1-like branch with the coupled criterion. Just to conclude the main result, For ceramic materials, if the size of the defect is small, you can ignore the defect, and it is possible to identify the factor parameters from 2 experimental tests. Okay, thank you very much.